There, yeah.
Yeah.
So let us start today's session. In today's session, we are going to look at the second part of thermodynamics. Basically, here we are actually dealing with the heat and the motion of heat, to be precise.
Mm-hmm.
So we'll be understanding that what is thermodynamics. Then we'll be talking about some laws. So there are basically three laws: zeroth law, first law, and second law. We'll be talking about internal energy and work done and other related things. So this session is going to be very interesting. All you need to be stay focused. Let us start with thermodynamics. That what is thermodynamics? As I told you, thermo means heat and dynamic means in motion or in transit. So whenever there is a heat and that is in motion or in transit, the whole branch of physics deals with this part is known as thermodynamics. So there are two terms that we need to understand first, that what is system and what is surrounding. Because in order to study the change or the transfer of heat, so we need two components. So basically what we did is a system is something which is going to lose or gain heat. Similarly, surrounding is also something which is going to lose or gain heat. So whenever there is exchange of heat between system and surrounding, that thing comes under thermodynamics. So generally heat transfer takes place between the system and the surrounding. So if we just consider any system, like for example, if you have heat some milk and you just left it at the room temperature, so what we see is that the container which contains the hot milk will going to lose heat, and that heat which is lost by the container is gained by the surroundings of the room in which it is kept. So that is something we can call system as well as the surrounding. So in thermodynamics, there are many types of systems and we need to understand it. Before that, let us define that what is system precisely. So the system which can be represented in terms of some physical quantities, let's say pressure, volume, and temperature, is something which is known as thermodynamic system. So whenever we are going to explain system, we do use these terminologies like pressure, volume, and temperature because these are the characteristics who defines the system. We'll
Mm-hmm.
be letting this know in detail in this class later on. Let us see what are the types of system do we have. So there are basically three types of system. Let us understand each one by one. So the first is open system. So as you can see, the name suggests a system which allows exchange of heat as well as energy.
Mm-hmm.
So you can say it allows exchange of heat and mass to be precise. Next we have is closed system. The closed system is the one that allows only exchange of heat, not the matter, not mass, or you can say matter. The last one is isolated system. The isolated system is the one which doesn't allow any of these. So basically, there is no exchange of heat, neither matter. Now, let us try to understand it with an example. So let me just give you the example of an isolated system that will automatically clear the open and closed system type. So just think of a thermos flask.
Mm-hmm.
So whenever you put anything into it, like a cold water, hot water, cold water, or whatever type of liquid, what you see is that over a period of time, the temperature of the liquid inside the thermoflask will almost remain same.
Mm-hmm.
Although it's not 100%, like there is no exchange of it. It isn't like that there is no exchange of heat, like 100%. But yes, most of the heat is stays inside that liquid only. So that kind of system is something we can say isolated system, which is completely isolated from the surrounding. So it is not related with like exchange of heat takes place between system and surrounding.
Mm-hmm.
So these are the basically three types of system, and here we are going to talk about it. We are going to use these terms in this chapter later on as well. Similarly, when we discussed types of system, they are also we talk about walls. Like basically, you can say a wall is something which connects system and surrounding, which allows whatever amount of heat or energy is going to exchange between the system and surrounding. So the walls are, which is linking between system and surrounding, are generally of two types. The first is adiabatic wall, and the second is diathermic wall. So again, this is completely new. You might have not heard this term before.
Yeah.
So adiabatic is something which doesn't allow anything to pass between system and surrounding. So suppose if
Mm-hmm.
there is a system and some surrounding, so the wall of this system, if it is adiabatic, so the exchange between system and surrounding will be zero. If this and if the wall is diathermic, so the exchange of heat will takes place between the system and surrounding, and such boundaries are basically called diathermal. So here there is these walls doesn't allow any exchange of heat and mass or heat and matter, whereas diathermic walls allow exchange of heat only. So now I can ask this one thing. So in the isolated system, which kind of wall must be present between the system and surrounding? What can you say about it?
Mm, the diet.
No, no. And the question is, which kind of wall is there between the isolated system and the surrounding?
Um,
Adiabatic or diathermal?
um, oh, adiabatic. The adiabatic
Yeah,
wall.
yeah, exactly. So this is the wall which actually creates that system to be an isolated system. Otherwise, if there is no adiabatic wall, we cannot say that system is isolated. So this is the wall. It is the wall that makes system isolated. If the wall is not adiabatic, the system won't be an isolated system.
Mm-hmm.
So again, system is in the reference of which is going to lose or gain heat. Basically, the system is something which is being studied by us. So that is something we call system. All right, let's move forward. So in this chapter, we have to also understand some variables, that what are the thermodynamic variables and how the change will affect the system completely, and how the change will affect the exchange of heat between the systems and surroundings. So the thermodynamic variables are basically classified by two ways. The first is state variable or state function, we call it, and the next second is path function. So these terms again, I can say they are completely new. Let us try to understand that what these two terms means. So state variable or function means, like for example, if you talk about the state of matter, we know there are three types of state: solid, liquid, and gas. So whatsoever variable which is linking between solid, liquid, and gas. are something we call state variables. These variables are something which doesn't depend upon the path. Like now, how this word path came. So suppose I changed solid into liquid. So in order to change solid into liquid, we must have to increase the temperature, right? If
Mm-hmm.
temperature is being increased, then only we can convert solid into liquid. So by whatever means we increase the temperature, that is something we call path. So state variable of function is something which doesn't depend upon the path. It only depends upon the initial and final state. So these functions are internal energy, pressure, volume, and temperature. So pressure, volume, and temperature are something which we are already aware of. Let us
Mm-hmm.
understand what is internal energy. So internal energy is something which allows a particular type of matter to perform some work, to do some work based upon what energy it already possesses. Like for example, suppose you didn't eat food for next 2 days. On the very third day, you will be able to walk. How you'll be able to walk? By the amount of internal energy your body possesses. Like that internal energy is something which is there in the body or which can be used to perform some work. But whatever food we are eating, that energy we are getting from the food, that chemical energy is something which is there in the food and we are extracting it from it. Whereas the internal energy is something which is always there in which is always there in a particular object or even us, you can say. Let
Mm-hmm.
us try to understand it again. So what we have seen is, suppose there is a dam. What does dam do? Why do we have dams?
It stops the water from like the ocean and stuff flowing in, and then
So basically, yeah. So basically, it alters the flow of water, you can say. And
yeah.
generally, how water flows? Water flows from high altitude to lower altitude, like in plains, and later on it went to the sea. So when we construct a dam, what we are going to do is we're going to use the energy of water, or to be precise, we're going to use the potential energy of flowing water. So that potential energy of flowing water is being used and it is being converted into electricity
Mm-hmm.
by whatever mechanism we have. So how dam is able to produce the electricity? Dam is able to produce the electricity by using internal and by converting internal energy of water into electricity.
Mm-hmm.
Again, always remember energy is something which cannot be created, cannot be destroyed. It can only convert it from one form to another. So
Mm-hmm.
whatever type of energy we are looking at, it can only be converted. You cannot create it, you cannot destroy it.
Mm-hmm.
Although you can do is you can use it and transfer it to something else.
Mm-hmm.
Next is path function. So path functions are some sort of thermodynamic variable which actually depend upon the path. It is something work and heat. This is for example, it's work and heat. We'll talk about work in detail. And if you think what is heat and how can we define it as a path function, so you can simply assume, suppose you are cooking something in a frying pan and the metallic handle it has is something made of metal. Now,
Mm-hmm.
metals are what? Metals are good conductors, right? So whenever you're cooking something and the whole frying pan is on the induction or something, you observe that the handle or the part of the frying pan with which you hold it, it also becomes hot slowly, slowly. How we can see this? How we can see this? We can see it by this thing that heat is something which travels, which always travels. And in that case, in the case of frying pan, it travels from the center. And at some point of time, it will reach the handle of the frying pan and ultimately it heats it. So heat is something which depends upon the path. If there is no path to reach here, you won't see hot metallic handle. Whereas in some cases, in some utensils, what we observe is that there is some plastic there at the top of it, which doesn't allow heat to pass from it. So heat is something which depends upon the path. If the path is conducting, then only it can be transferred. If the path is not conducting, or if the path is something which doesn't allow heat to flow, you won't see that heat is flowing. So these are
Mhm.
the two things: state variables, state functions, or path functions. So when it comes to work, we'll talk about it in the upcoming slides.
Mhm.
Let's move ahead. Also, the thermodynamic variables can be classified with two other ways also. The first is extensive variable, other is intensive variable. Extensive variable is something which can be changed with change in whatever size of system we has. These are the variables which depends upon the quantity. So the volume, mass, internal energy is something which depends upon the quantity. So this is something we can say the another way of describing thermodynamic variables. Similarly, we have some intensive variables also. Intensive variables are those which depends upon the size and quantity both. Example,
Mhm.
pressure, temperature, and density, you can say. So
Mhm.
these terms are basically those terms which we are going to use later in this chapter, and we should know that what kind of variable they are. Either
Mhm.
they are state function, either they are path function, or we can also describe these two as extensive variables and intensive variables. So always remember when it depends upon the quantity, it is extensive. When it depends upon the quantity as well as size, like
Mhm.
it doesn't depend upon the quantity as well as size, then we can say it is intensive variable. So volume is something which depends upon the quantity. We cannot describe volume without knowing the quantity. Whereas density is something which is constant for entire volume. Like if we assume seawater and we try to find out the density of seawater, what we see is it is constant throughout the globe. It's not like that in Pacific Ocean, it's different, in Arabian Sea, it's different. It's same. Everywhere it's same. So density
Mhm.
is independent of the quantity, you can say. So that is how you can define intensive variables.
Mhm.
Let's move ahead. So here the chapter begins and we'll start with zeroth law of thermodynamics. So if you have seen some sort of laws in previous chapters of physics in earlier classes, you must have seen that the laws start from first law, second law,
Mhm.
third law. But here in thermodynamics, only here we see the zeroth law. Let us understand that why there is zeroth law. So what happens here in physics is that if something is given by some scientist and it is fundamentally correct, it is there, it exists everywhere in the universe, and that is something regarded as, let's say, first law. So you cannot change it.
Mhm.
It is something we cannot change it. But when scientists found about this particular phenomena, which is explained by the zeroth law, they said it is more fundamental than the first law. So as it is more fundamental, it is more viable to understand. So they just coined the term zeroth law, which doesn't
Mhm.
exist before, but after this it exists. So when you are able to distinguish between the first law and zeroth law, you'll be able to see that yes, zeroth law is more fundamental. Like let us understand, let us try to understand. Suppose we have three systems, A, B, and C. Temperature of system A is TA, temperature of system B is TB, and temperature of system C is TC.
Mhm.
Between the system A and B, we used adiabatic valve. What is adiabatic valve?
Um, when there's no, there is an exchange of heat, and or is that the other
When
one?
there is no exchange,
Mm.
neither of heat nor of mass or matter. Whereas in this in between system AC and VC, it is diathermic valve. So It allows exchange of heat.
Oh, I confused the two. Okay.
Yeah. So if there is exchange of heat between system A and C as well as between B and C, so can I say that at some point of time, temperature of A will becomes equals to temperature of C as well as temperature of B will becomes temperature of C? Like this is something which is allowed by diatomic walls only. The first law of thermodynamics says if temperature of system A is equal to temperature of system C as well as temperature of system B is equal to temperature of system C,
Mm.
then temperature of A must be equals to temperature of B. Like
Okay.
that much fundamental it is.
Mm-hmm.
Like it's simply math, it's simple math. If A is equals to B and B is equals to C,
And
then
eight.
A must
Yeah.
be equals to C.
Okay.
So we just write it in terms of temperature of three systems. This is what the zeroth law of thermodynamics says. If two
What
bodies are in,
did you say? T. Oh, yeah, yeah. Okay, yeah. Mm-hmm.
so this is what zeroth law of thermodynamics says. If two
Mm-hmm.
bodies are in thermal equilibrium, thermal equilibrium is another term which is used to explain that both the systems are connected with diathermic wall, or you can say that the temperature of system A is equals to system C. This is what it
Mm-hmm.
explains. This is what thermal equilibrium. Whenever there is an equilibrium term, so just it should come to your mind that when we are talking about similarity, it can be of any type, like you can say the similarity of temperature, similarity of whatever the type of force they are experiencing, similarity of anything which is there in physics. So
Mm-hmm.
equilibrium terms means system A and system B are similar. In what sense? You don't know. The term before the equilibrium will make us understand that what kind of similarity we're talking about. So if two bodies are in thermal equilibrium with third body separately, like this, A is in thermal equilibrium with C, B is in thermal equilibrium with again C. Then the two bodies will also be in thermal equilibrium. So the temperature of A and B is also equal. This is what the zeroth law says.
Mm-hmm.
Next we have is internal energy. Just like I said, so we are going to review this as well. What is internal energy and how does it affects the other things? So let us try to understand it. So it is the energy of gas due to molecular motion. Whenever there is molecular motion, like suppose this is the container and this container has different gas molecules. So these gas molecules will be moving randomly. So whenever there is motion, the energy associated with the motion of body is kinetic energy. Always remember this. Whenever there is motion, so the energy associated with that motion is kinetic energy.
Mm-hmm.
Similarly, if we're talking about the configuration, like for example, suppose I have constructed a bridge in multiple ways. Let me give you some of them. This is one such way of constructing it, and you can assume this is another way of constructing it.
Mm-hmm.
Like what I means to say is that you have seen that there are multiple ways of constructing a bridge. But
Mm-hmm.
did you ever thought that why this particular type of bridge is there in this particular situation? Basically, the thing is every type of bridge is constructed depending upon the location. Also, every type of bridge holds different potential energy, like whatever which amount of energy it can hold or whichever amount of energy it can persist. It will depend upon completely on the configuration of it, or you can say the interaction. So here, whenever we are talking about the internal energy in respect to the gas, we'll be talking about kinetic energy as well as potential energy. Kinetic energy is something which is associated with the motion, Potential energy is something which is associated with the interaction or configuration of the system. Again,
Mm.
configuration means that how does it looks like, how does it made, how many, in which container it is kept. So all these things are known as the potential energy thing. Let me just explain it in a different terminology as well. So internal energy is something which is denoted by capital U. Whenever we are talking about energy, we are going to use U as to
Mm.
represent it. So internal energy of a system is nothing but the sum of kinetic and potential energies of the molecules of the system. It is generally the function of temperature and volume. Let me show you. So internal energy is generally the function of temperature and volume. Also, in case of an ideal gas, intermolecular forces are zero. This is what we studied yesterday. So if intermolecular forces are zero in case of ideal gas, so there will be no potential energy because potential energy is due to the interaction and the configuration. So we can say for potential energy to exist, there must be some sort of interaction between the molecules. And if it is ideal gas, there is no interaction, so there will be no potential energy.
Mm.
Does it make sense?
Yeah.
Remember this internal energy is a function of temperature and volume. Like it depends upon these two things. You cannot explain the thermal energy without temperature. You cannot explain the potential energy without knowing the volume.
Mm.
So we generally write U as energy due to kinetic energy and energy due to potential energy or the configuration. So this
Mm.
is how the internal energy is being given. And for ideal gas, UP is zero. Like potential energy is zero. All right, let's move ahead. Next, we have to work. We have to discuss about work done. So here specifically, we are going to discuss about work done by a gas. How much work done a gas has capability to do. So in order to understand it, let me just draw one such diagram. So suppose this is a container, and in this container there is this piston. There is this piston, and we have gas molecules in it. So initially it was stable. We didn't do anything. But later on, what we did is we heated it from the bottom. So whenever we are heating it from the bottom, what will happen next? The particles of
They'll
this
move around.
container, they will get some thermal energy. And
Mm-hmm.
because of the thermal energy, they will start moving randomly with more velocity. And ultimately, they are going to strike the container. They're going to exert the pressure. And
Mm-hmm.
because of which, this piston will be forced to move up. There will be some force because of which this piston will move up.
Mm-hmm.
So we have to find out that how much work this piston has done. This pressure, external pressure, has done. So in order to find the work done, we have to assume that there is some displacement, like there is some movement of the piston, and we can say that it moved by some dx distance. Again, this is what this is displacement. And this displacement of this piston is due to the pressure.
Mhm.
So we have to calculate that how much work is being done by this external force which is there due to the pressure thing. So in order to understand it, we have to first of all see that what is work done. Like in physics, we define work done as, suppose this is an object and you applied some force on it. What will happen to the object? Because of the force, this object will displace.
Mhm.
And because of this force, this object displaced by some distance x.
Mhm.
So work done by this force is nothing but force into displacement. This is the basic idea that you need to have about work done.
Mhm.
So when we are talking about work done here, because of this external pressure, so work done is again nothing but force times displacement.
Mhm.
You just tell me one thing. Do you have that idea about calculus?
Yeah, I did calculus this year. So
So what were the topics you studied in calculus?
in calculus, it was like derivatives and also antiderivatives, and then um like A rock, I rock,
All
and
right. Just tell me the derivative of this.
is this using the chain rule?
Yeah.
Okay, because I struggle with chain rule. Um,
Why? It's
I
the
find
most
that one
basic.
the no, I find chain rule the trickiest one
There is nothing tricky in chain rule. Okay, just tell me what is the exponent in this equation?
too.
What is the angle in this equation?
3x.
You know this thing, then there is nothing to think about it. Let me just give you the idea. In this trigonometric functions, how you have to apply the chain rule? First, you have to differentiate power like exponent.
Mhm.
It should be followed by the trigonometric base, whatever base it is. Then it should be followed by the angle. Like first you have to derive a derivative. You do the derivative of power, then you have to do the derivative of base, then you have to do the derivative of angle. So if I'm assuming this is my y and I want to differentiate it, so I'll simply multiply the whole equation by d by dx, as x is the variable in this equation. So what we were supposed to have, d by dx is nothing but, first of all, we have to do the derivative of power. So how do we do it? Power,
Bring the power
power,
down, and then the
bring it
base,
down, then
and
write the base as it is by subtracting 1 from it. So
mhm.
cos square, 2 minus 1 is 1,
Yeah,
cos 3x. So the power thing is done. Derivative of power is done.
and then
What you
times
can
the
do is,
derivative of 3x. Or no,
yeah, then you have to do this. So you can do it in a single step also. If you are struggling with it, just I suggest just do it in multiple steps. So what is the derivative of cos x?
cos x or cos 3x?
I'm asking you the cos x
um. Oh, minus sine x.
minus sin x. Correct. So it will be minus sin 3x.
Yeah, minus sine 3x.
Then we're done with the base also. Again, I'll write d by dx of base, d by dx of angle.
Mhm.
So the final answer of this equation is, now what is the differentiation of 3x?
It's just three.
It's just 3, correct.
It's
So the
just three.
final answer is going to be cos 3x sin 3x.
Mm, yeah.
Why?
Oh.
There is nothing tricky in this. So if you know the derivative part, you should also know antiderivative of it. Can you do the
Mhm.
antiderivative of it?
Um, I kind of forgot how to do it.
Yeah. Do you have maths in this semester?
I do, but I'm taking statistics.
Like what it is? Exactly. What it is exactly? You're
Um,
taking what?
I'm taking statistics.
Statistics. Okay.
Yeah.
All right. So basically, I was talking about work done, and work done is nothing but force times displacement. See, calculus is something which is being used here in physics like a lot. Without
Mhm.
calculus, you cannot even think about any equation in physics. So
Mhm.
ultimately, we'll be using calculus to derive infinite relations here in physics. Basically, mathematics is the tool. It is the
Mhm.
tool which is used to explain what are the things exactly happening in physics.
Mhm.
Without without maths, we cannot have any other way of expressing the equations of nature or the universe. So we ultimately need it. Like for example, so work done is something force times displacement. So if there is some small displacement, so the work done for it would be again a small work. So in order to write that, what we have to do is we will write dw. Force will remains F, displacement is going to be dx. So in order to get the complete work, what we need to do is we need to antiderivative it or the integrate it. Let us see how do we do this. So what you can see here is like this was the container. That container initially it has piston at this level. Later on, we found that because of the change in energy, the piston rises to this particular level. So look at the equation. So dW is nothing but F times displacement. This displacement we can say.
Mhm.
So can you think of what we can write in place of force?
Mm.
Like cause of this force, the gas is exerting pressure, right?
Mhm.
So if you know that pressure is nothing but force per unit area. So what we can write in place of force? Pressure times area.
Yeah.
Write this. So I'll be substituting pressure times area with this. So just think of it. This is the displacement. This is the area. So this much is the change that is produced.
Mhm.
Like this much is the change.
Yeah.
So what change it is? It is something we call change in volume. Because here the entire piston moves up. So because of that entire piston's motion, can I write this A times dx as volume?
Mhm.
Like what is volume? Volume is nothing but area times height or the length you can say.
Mhm.
So in this case, the area of the piston is A. The displacement of the piston is something dx. So in place of A times dx, we can write volume. So
Mhm.
ultimately, what
Heat.
we have is that dw is nothing but P times V.
Times. Yeah.
And to be specific, it should be dV, not V.
Mhm.
So in order to have the complete work, we have to integrate these equations. Now just think and tell me, how do we integrate?
Mm. So P times A times D's. Um.
No, no, no. Just think here, just see here. So just look at the diagram. This is the first figure. This is the second figure. In the first figure, when there is no heat given to the system, there is no extra pressure, so the piston stays where it is. So can you say that initially it had some volume? We can write VI.
Mm-hmm.
When we applied that extra, you can say heat to the system, when we give the extra heat to the system, what happens with the system? Its volume increased. It
Mm-hmm.
becomes some V function. This is what this diagram says.
Mm-hmm.
So when there was initially some volume, the work done by the system or the piston is zero. But when we have some final volume Vf, there must be some work done. So this is how we are supposed to write the limits. Now let us just conclude it. So when we integrate this whole thing, we'll get W is nothing but P times P final minus V initial, like that. So this is the equation of work done against the piston. So this is the relation of work done which we are going to use in this particular unit.
Mm-hmm.
All right, just think again and tell me what is work done. What do you
It's
understand by work done?
um it's just force times displacement.
This is not the definition that we use to explain work done. So work done is something we can say whenever there is some force, and to be precise, some external force.
Mm-hmm.
So that external force does what? It does displacement.
Mm-hmm.
So whenever there is displacement due to some external force, we simply say that there is some work done.
Oh, okay.
So for work done to be there, there should be some external force, and because of that external force, there should be some displacement. Then only we'll say that there is work done.
Mm-hmm.
Let me just give you that example. Suppose it is a wall. You're standing against the wall and you're pushing it with some force.
Mm-hmm.
Will you able to push the wall?
No.
So can I say that you haven't applied any force?
No.
You must
You
have
have
applied some
applied
force,
the
but your
force,
force was
but it didn't
not.
get displaced.
Yeah, you applied the force, but your force wasn't enough to displace the wall. But in physics, work done is only considered when there is some displacement.
Mm-hmm.
So physics will not consider your application of force as any work. So this
Mm-hmm.
is the thing. So here also, if you just look at the whole thing, whole scenario, who actually does the work here?
The heat.
Correct. So heat is the one who does work. Or to be precise, that heat in transit does this work. If we don't have heat, this whole work is not possible.
Mm-hmm.
All right, let's move forward. So the first law of thermodynamics, a very basic law, but you can say the equation sometimes people doesn't remember. This is a law which is based upon conservation of energy. Like conservation of energy is something which is there like in almost every chapter. In every unit, we are somewhat relating that conservation of energy thing. So just remember this. Let us try to understand again with an example that what does this first law of thermodynamics says. Suppose what I did is I had this metal sheet with me, and this metal sheet has lots of electrons in it. And some of the electrons are capable enough to leave that sheet somehow. So what happens here is you started heating it. with some sort of energy, like whatever form you can use. Let me use that I uses sunlight to heat that. So what does this sunlight do? Whatever amount of energy that sunlight carries and give it to the surface, some electrons present on its surface will absorb that energy. Some part of energy is being used by the electrons to escape from this metal surface, and the remaining energy of those electrons will be converted into kinetic energy. Let me
Mm-hmm.
give you another example. I guess this might be a little difficult to understand. One more example. Suppose there is a block. What you have to do is you have to take this block all the way up
Mm-hmm.
to some height. So what you're going to do, first of all, you need to have some energy to do that work, right? Without energy, you won't be able to do any
Mm-hmm.
sort of work. So suppose some way you got that energy, and I'm writing that energy as Q.
Mm-hmm.
So what you did is using that energy Q, you are able to put that box all the way along to the height edge. So what would happen here is that because of that energy, first of all, you did some work. Because of that energy, you did some work,
Mm-hmm.
and the remaining energy will be there in the form of your internal energy.
Mm-hmm.
Like again, the first law of thermodynamics says whatever amount of energy is supplied to the system will be capable of doing work from that energy.
Mm-hmm.
And after doing the work, whatever amount of energy is left will be stored in the form of its internal energy.
Mm-hmm.
So if heat is given to the system, that system will do some work, and out of that work, some part of energy will store in the form of its internal energy. So this
Mm-hmm.
is that first law of thermodynamics means. Like it simply says energy given to the system is equals to some work done by the system plus internal energy of the system.
Mm-hmm.
Let me give you some another examples of it as well. So suppose you're cooking rice again in a pressure cooker. So what you does is you heat the pressure cooker,
Mm-hmm.
like you are supplying some energy to it. So what does this pressure cooker do? It will take that energy Q, some part of energy Q will be used in doing the work done,
Mm-hmm.
like work done to cook that rice.
Mm-hmm.
And the remaining energy will be stored in the form of internal energy of the rice. That's why we see that the rice is hot when we just look at it after cooking.
Mm-hmm.
So why is it hot? Because of the internal energy. Some part of energy is being used to do the work in order to cook the rice, and another part of the energy is being used or it's being stored in the form of its internal energy. Like this law is very simple. Suppose you get some sort of energy, some part of energy you can use for the work done, and if your work is done and still you had some energy left, so that energy is being stored as the internal energy. So
Mm-hmm.
that is what this whole thing says. Whole first law of thermodynamics says. So it is a very basic and you can say the prominent law. Initially, it was the law. It was the law which was given first,
Mm-hmm.
but Later on, when we found that zeroth law statement is more fundamental, so we just termed that coin zeroth law. Otherwise, we would have given it as second law, but second law is something which should be advanced or which should be more uh, different from it. It defines some other factor, but that zeroth law is something which doesn't shows us this more fundamental, more basic. That's why we're just using it.
Mm-hmm.
So let's move ahead, and we got these three quantities: delta Q, delta W, and delta U. Delta Q is heat, delta W is work, and delta U is internal energy. So here what we have is sign convention. Like sometimes we take it as positive and sometimes we take Q as negative. So what are the conditions? Similarly, sometimes we take work as positive and sometimes we take work as negative. Similarly, sometimes internal energy is taken as positive and sometimes as negative. So what are the conditions that we want to see it? So heat is taken as positive when it is supplied to the system.
Mm-hmm.
Like this is something we're going to use in the numericals, so that is why it is important. Whenever the heat is supplied to the system, it is taken as positive. Next, it is taken as negative whenever we are drawing heat from the system. So whenever you have taken out something from the system, it will be taken as negative. Work done is taken as positive when work done by the gas, when gas is doing the work done, like expansion, just like we saw in the previous slide, that gas expands because of that volume increases. And the
Mm-hmm.
work done is taken by negative when work is done on the gas. Somehow we are able to compress the gas. So that
Mm-hmm.
is called compression. So that is the case where work done is taken as negative. Similarly, we can say the internal energy is positive. There are a few conditions. With temperature increase or temperature rise, we can say internal energy is positive.
And then when it's a
Similarly,
decrease in temperature, then it's negative.
exactly. When temperature falls, so it will be negative. So these are the terms, these are the sign conventions which we are going to use and doing when we are doing numericals. Let's move ahead. All right. So what can you say about it?
It's B, conservation of energy.
Correct. Next. Any idea? You can do it, I guess. Try it out. I guess you can do it.
Mm.
Let me give you that conversion. 1 kilocalorie is something equivalent to 4184 joules of energy.
Mm-hmm.
So this question says that the internal energy change in the system that has absorbed 2 kilocalories of heat.
Mm-hmm.
So this is the energy which is absorbed by the system. So this is something we can call Q, 2 kilocalorie. In order to solve it, we have to convert it into joules, and the conversion is this. 1 kilocalorie is 4184 joules, so 2 kilocalories would be 2 times 4184. So
Mm-hmm.
that much joules is something which is being absorbed by the system.
Mm-hmm.
And because of the energy, the work done by the gas is 500 joules. The question is asking us to find out the internal energy. So what was the equation from the first law? That Q is nothing but work done plus internal energy. So
Mm-hmm.
internal energy is going to be work done heat minus work done. So
Yeah.
8
8368 minus
minus,
500.
and it is going to be
7868. So approximately 7,900.
exactly. So that much amount of internal energy would be there for this system. Let's move ahead. Now, there are some thermodynamic processes. There are a lot of processes. Let me just give you the name. It starts with isobaric. Isobaric is the thermodynamic process which says that the pressure throughout the system remains constant.
Mm-hmm.
Then we have isochoric. Isochoric is a system in which the volume is constant throughout the system. Then we have isothermal. Isothermal is a system in which, yes,
I think I've heard of isothermal, yeah.
yeah, you must have heard it in chemistry.
Yeah.
Isothermal is something which in which temperature remains constant.
Mm-hmm.
Then we have adiabatic process. Adiabatic process is something in which there is no exchange of heat. So
Mm-hmm.
these are the major systems of the processes. And last, we have some cyclic processes also, in which the energy transfer is happening in such a way that it will return to its original source.
Mm-hmm.
So I don't know whether these systems are there like a lot. So I'm just here to give you the overview. And if there are these systems, like you have to understand it or learn it with greater depth, then we can think of it. So isobaric is something where pressure is constant. Isochoric is something where volume is constant. Isothermal is something where temperature is constant.
Mm-hmm.
Adiabatic is something where Q is constant, no change of heat. And cyclic, in which the process repeats itself after certain period of time. That is cyclic process. Also, there are two more types of processes. You can say a reversible process and irreversible process. So as the name suggests, some processes might be able to reverse themselves and some cannot. So that is reversible and irreversible. All right, let's move ahead. This is the most important part that we need to discuss. I guess it's time and we should just hang on over here. We have some topics left and we need to discuss them also. We'll do it in tomorrow's class. We'll start it from here only,
Mm-hmm.
like specific heat and heat capacity. And we'll talk about it, how it goes. We'll do some numericals also in tomorrow's class, discussing that how can be solved, how these things can be solved.
Mm-hmm.
Till then, what you can do is just revise all those things. And if
Yeah.
there is something that you want to ask, we'll discuss accordingly.
Okay. Yeah.